underground labyrinths. Super-sized machines rip deep into the earth. Gargantuan scoops lift thousands of tons from massive open pits. High-tech operations extract a resource that accounts for half of our electric power. Now, coal mines on Modern Marvels. To reach their work site, miners at the Camp Creek mine in East Lynn, West Virginia, must travel 7 miles through the insides of a mountain. The workers ride a rickety rail cart through a long, cavernous tunnel that is their highway. After their 1-hour commute, they finally reach the working face of the mine. Here, a monstrous machine with foot-long teeth chews away at the earth. This is one of the most efficient underground mining methods ever developed: continuous mining. This technique accounts for almost half of the coal retrieved by underground mining today. The machine, called a continuous miner, cuts up the seam of coal from the mining face, eliminating the need for blasting or drilling. It has a large rotating drum-shaped cutting head that spins and breaks the coal from the seam.
We're at the front end of the continuous miner. This is the end of the miner which actually breaks or extracts the coal from the face. As you can see, there's an 11.5-foot drum on the front of this miner. It rotates. It has bits laced on the drum in a scroll fashion.
This continuous miner can mine in 1 minute what took a miner in the 1920s an entire day to produce. These powerful machines are remote controlled.
Every day we'll cut about 250 foot with each miner. This remote, you can work anything on this miner that you could with sitting in a day. You turn the head on, you can raise it up and down, you can turn the conveyor on. Anything that you can need to control on that miner can be controlled through this box.
The machine has moving arms that scoop the coal directly onto a conveyor that leads to a shuttle car. A miner then drives the shuttle car to a longer conveyor that carries the coal to the surface.
A continuous miner is going to have different productivity rates, but typically 6,000 raw tons a day would be a reasonable expectation.
200 miles away in the Bailey mine in Wayne County, Pennsylvania, an even more impressive machine is hard at work: the longwall. Longwall mining is another approach used in underground mines. Perhaps the most productive current underground mining method. Unlike the continuous miner, the enormous longwall cuts across one very long seam of coal that is broken apart by a rotating drum that sweeps back and forth. The coal falls directly onto a built-in conveyor. This technique can recover up to 40,000 tons of coal per day. Longwall machines have revolutionized underground coal mining.
The longwall machine has a series of cutting heads or shears that chew away at the coal. They got cutting bits on it and they break the coal. It falls onto a belt line. That entire coal seam is removed, and these panels are about 1,000 feet wide on the average, and they will sometimes run as much as a mile. I call it Star Wars technology.
Early versions of the longwalls were developed in the late 1950s. Today, the machine is completely automated. It has a hydraulically operated steel canopy that keeps the roof of the mine secure and moves along with the machine as the coal seam is cut. The roof in the mined-out areas collapses in a controlled manner.
If you can imagine the early days where you were extracting the coal using a pick, using a shovel to load it into a wagon that was pulled outside by a pony, is significantly different than using a remote control with a joystick to operate a 600 horsepower continuous miner.
Today's underground mines look much different than they did years ago. The Camp Creek shaft mine in West Virginia is no exception. The walls of the tunnels of this deep coal mine are surprisingly white instead of black. This is due to the application of rock dust, which is ground up lime that is sprayed to the mine roof, floor, and ribs to help prevent mine explosions. Limestone dilutes any hazardous concentrations of coal dust, which can cause explosions. Large ventilating fans also remove any lingering coal dust, as well as methane gas.
From the surface, huge ventilating fans are used to cause a pressure differential to pull atmospheric air from the outside into the coal mines. Ventilation does primarily two things: removes gases from the mining areas and helps to control and reduce dust. As you can see here, a ventilating curtain is used to direct air in the working faces to where the employees are performing their duties.
Coal deposits exist on every continent, including Antarctica. It is the fuel most widely used to produce steam to drive the turbines of power plant generators. When coal is burned, the carbon and hydrogen naturally found in the fuel combine with oxygen to produce carbon dioxide and water vapor. This reaction gives off heat energy.
About 55 to 56% of the electricity that people use in this country is made by burning coal.
The electric utility companies use more than 80% of all coal mined in the U.S. The concrete, paper, and glass industries also consume large quantities of coal as a fuel for heating and powering their facilities. The steel industry is reliant on coal to produce coke, a hard carbon material used in the manufacture of iron and steel. The carbon in coal gives steel its strength and versatility.
Steel is the sinew of modernity. For railroad tracks, locomotives, automobiles, steamships, the girders in skyscrapers, steel and the coal that was used to heat the iron to make it are the essential ingredients, an abundant source of economical power to create the modern world as we know it.
These impressive technological advances are the culmination of a coal mining effort that reaches as far back as 3,000 years for a resource that was formed millions of years ago. Affectionately referred to as buried sunshine, coal is a fossil fuel formed from vegetation that grew in swamps as long as 400 million years ago. This vegetation absorbed and captured the sun's energy and sank to the bottom of marsh areas to decompose into a soggy, dense material called peat. As the surface of the Earth changed, geological forces buried the peat under heavy layers of rock. The continuing pressure and heat transformed the compressed peat into coal. When the coal is uncovered, it is located in strata, or seams like the filling in a multi-layered cake. Early civilizations found ways to mine this buried fuel long before it became an ample source of electric power.
The first records we have of coal being used, and therefore presumably mined, date back about 3,000 years ago. Coal was used for funeral piles in Wales. The Chinese probably used it around the same period. And Aristotle records the rock that burned. So we think that somewhere between probably 3,000 to 2,000 years ago, coal mining started. We have no record of how it was mined at that point, but we assume that they simply mined the outcrops of coal where it appeared on the side of a hill or a cliff.
Before 400 AD, coal was burned and used as a source of heat during the Roman occupation of Britain. And it was being used in America as early as 1000 AD by the Hopi Indians in what is now Arizona. They also used coal for heating purposes and to bake their pottery. Scholars believe that laborers and peasants, both in England and America, dug small surface pits for domestic fuel. But for the most part, wood was still the main source of fuel.
The first recorded mining of coal that we have written record of refers to sea coals. Sea coals occurred along the beaches of Scotland and northeastern England, and were simply picked up where coal seams basically occurred on the cliffs. As the coast eroded away, the coal would have appeared on the beaches like any other rock. It's apparent by the 13th century that sea coals were the first coals actually taken down to the big cities, London being the major one, as a source of fuel.
London was starting to run out of firewood, so this sea coal became a popular replacement. The increased need for coal in other parts of Europe during the same period was a direct result of the diminishing supply of forests and wood as fuel. Great emphasis was placed on the development of the coal fields due to the economics of the time. Coal simply became a cheaper fuel source than wood at that point. Miners would now have to dig to provide an adequate supply of coal to keep up with the new demand. Next, with new methods of retrieval, coal becomes the main source of fuel in the world, but not without a price. As the forests of Europe began to dwindle, coal emerged as the only other source of fuel. Early miners needed to find new ways of extracting it. The bell pit method of coal mining evolved as early as the 14th century, when monasteries and castles used coal for domestic purposes. The name comes from the final shape of the excavation. Miners dug vertical shafts straight down through the coal seam where they created a bell-shaped chamber that allowed them to extract as much coal as possible without the roof caving in. These narrow shafts were no more than 30 feet deep and presented few dangers. Explosives were not in use yet, so the miners broke through rock and coal with nothing more than primitive tools, such as stone hammers, picks, and shovels.
Coal mining originally was done by hand, pick and shovel. The coal was hacked out of the coal seam, put in baskets where small children or women could haul it to the surface. In a deep mine, a shaft with a winch crank at the top could lift buckets of coal out.
Ladders were used for access, and candles were the only source of light. The coal was sorted into different sizes, usually by the women and children. This mining method continued to be used for centuries. Drift mines evolved as another method of coal mining, starting in the 15th century.
Drift mining would have occurred where a coal seam disappeared into a cliff or a steep side of a hill, where putting in bell pits would have required the development of enormous shafts. And so the only way to mine the coal beyond the outcrop was simply to drive a tunnel in and follow the coal seam. And this would have been the start of drift mining, drift being the mining word for tunnel. The miners who drift mined, again, rapidly learned the basic rules of room and pillar mining. That is, you can't make an opening too wide or the roof will collapse on you, and you have to leave pillars of coal behind you to support the roof.
The most common form of injury and death was a roof fall in a coal mine. The deeper that a mine went underground, the more difficult it was to keep the top up, to keep the mine safe so that miners could get in and coal could come out. The simplest way to do that was to cut mine timbers, properly set in place with shims at the top and bottom to ensure a tight fit. That was the most common form of keeping the top off of the coal miner in the coal mine.
These coal mining methods remained relatively unchanged for several hundred years. It wasn't until the 17th century that England began to advance mining techniques. Up until then, miners hauled coal in wicker baskets on their backs, then in wheelbarrows or on sleds. By the mid-17th century, animals began to be used to pull coal carts in the English mines. England also introduced mine railway systems, as well as a reliable system to drain water and prevent flooding in the deeper mines.
As they mined out the near-surface coal seams and they went deeper, they started to encounter large quantities of water. And the systems that they had of pumping water were so primitive. What they really needed to solve the water problem was a source of power, a pumping system. Up until the 18th century, water wheels were the only real source of power.
In 1774, James Watt perfected the steam engine, which finally resolved the problem of efficiently pumping water out of the deeper mines. Although the American Indians had used coal found in small surface pits as early as 1000 AD, It wasn't until the Revolutionary War that more sophisticated coal mining operations appeared. Coal mined from small drift mines in Richmond, Virginia, was used in the manufacture of weapons for the American troops. Before the war, most of the coal came from England. But even after the American Revolution, Britain continued to provide America with coal through the early 1800s.
Coal was basically imported to the United States up until the War of 1812. In fact, Britain really discouraged the mining of coal in the United States. They didn't want anybody competing basically with Britain economically. And so what we have is we have this curious condition of coal being literally shipped across the Atlantic when there were enormous quantities known to exist here in the United States. But after the War of 1812, it took very little time before people started to mine coal here in the U.S., even though there was enormous quantities of wood.
The first record of continuous coal mining in the U.S. goes back to 1840 in the Richmond, Virginia coal basin. The Americans used the British innovation of huge steam pumps to drain water from the deeper mines. However, the other problem was the need to safely ventilate the mines and push methane out. Pockets of methane gas formed millions of years ago are trapped in coal seams and are extremely flammable when mixed with air, and often lead to deadly explosions. Until the introduction of steam and later electric fans, miners ventilated underground mines by creating furnaces at the bottom of the shaft.
The first working fan in an underground coal mine probably occurred in Belgium in about 1835. They were powered by steam engines, not very effective, but better than the alternative, which was typically the use of fires to ventilate coal mines. The idea is simply that the fire heats the air and, just as a chimney in a house, draws the air through the mine. If it's a gassy coal mine, when the methane gas hits that fire, as it will do in pockets on occasions, you can have an incredibly disastrous explosion.
Another problem the miners encountered underground was oxygen deficiency, also known as black damp. Enter the legendary canary.
The cage was actually used to carry canary in a coal mine, and the canary was there for what they call black damp. They found a long time ago that the canary would die in a low oxygen before a person would.
Miners would trim the canary's claws because they discovered that the bird could die from the lack of oxygen, but still grip its perch and appear to be alive due to the effects of rigor mortis. By the late 1800s, coal mining in America was one of the fastest growing industries, doubling every 8 years. Most of the mine operators owned everything else in the small, isolated mining towns, including the miner's home, leaving the workers powerless and vulnerable to unsafe conditions.
Roof falls in coal mines, underground explosions, fires. Coal mining was the most hazardous occupation in industrialized societies. The industry was slow to adopt a safety underground, believing that it would limit production and limit employment.
Large mining disasters followed the rapid increase in production. The European mines had already started to experience methane explosions with increasing frequency and with more tragic results as the number of miners underground grew. And as the mines got deeper, the methane content increased. Disaster struck American mines beginning in the 19th century. But the worst mine explosion in the United States occurred at Monongah, West Virginia in 1907. As many as 425 miners died when dynamite was improperly handled and a blast ignited the methane and coal dust.
The enormous number of fatalities that were occurring in mines due to explosions and roof falls and carbon monoxide and various other accidents. We had, as a result of that, in 1910, the U.S. government formed the United States Bureau of Mines. Its job was simply to do research and come up with improved technologies to greatly enhance the health and safety of mining at that particular time.
Flame safety lamps replaced the archaic canary in a cage. The flame emits an orange glow if methane is present in the mine. And if oxygen levels are low, the flame goes out. Separate ventilation shafts with powerful fans circulating air replace the dangerous ventilating furnaces. Coal dust was linked to black lung disease, also known as coal miners' pneumoconiosis, a progressive pulmonary disorder that builds up over years of inhaling high levels of airborne dust particles. Levels of coal mine dust began to be constantly monitored and controlled by wetting coal or by spraying limestone on the walls. These improvements had a great impact on reducing injuries and fatalities underground.
Coal mining's not even among the 10 most dangerous occupations. Mining is not. Coal mining today is very, very tightly regulated. But it took the cooperation of the industry, labor, and federal and state regulatory agencies to achieve that record.
Next, incredible advances in coal mining equipment lead to greater efficiency. With the advent of electricity in the latter part of the 19th century, the mechanization of coal mining began on a large scale. First, electric hammers and saws, then coal-cutting machines began to appear in the underground mines. But one man in particular would rise above the others by developing a series of new inventions that helped revolutionize underground coal mining. At the age of 12, Joseph Francis Joy followed in his father's footsteps and went to work in a coal mine in 1895. Frustrated with how hard and dangerous the work was, he became determined to find a better way. By the time he was 36 years old, and after many attempts, he invented the first successful mechanical coal loading device.
In 1919, we have the first of the mechanical loading systems that was really very, very effective, so effective that it's still widely used today, which is the Joy gathering arm loader. And this, again, was to really revolutionize mining at that point in history. These loaders would typically load into coal cars. The Joy loader was electrically powered and incredibly effective. It wasn't until the 1930s that, again, Joy came along and built the first of the shuttle cars.
Joy would go on to accumulate 190 patents in his lifetime, many of which drastically improved underground mining mechanization. One of the most important was an early version of the continuous miner.
In 1947, what we have is, again, Joy comes up with a machine, the first of the continuous miners, the ripper machine. The ripper machine basically tore up the coal. No longer did you have to undercut it, no longer did you have to drill it, no longer did you have to shoot it. What you now had is one machine that literally tore the coal down onto a gathering arm loader, and the loader simply then loaded the coal out directly over the back of the machine and into the shuttle cars.
Over the years, Joy and other engineering pioneers reconfigured crude and ineffective machines that would lead to today's highly efficient and productive underground mines. After the introduction of the shuttle car, roof bolting systems were developed in the 1940s. Roof bolts helped to prevent cave-ins in the underground mines. Miners secure the roof over the mined-out area by using a roof bolting machine. These bolts are long rods driven into the roof to bind several layers of weak strata into another layer that is strong enough to support its own weight.
If I took that coal miner that had been asleep for 40 years into a mine today, I think he would be wide-eyed and absolutely amazed at the mechanization that has occurred in the mining environment.
As the machinery evolved, so did the miner. Today's miner must have the proper attire before going underground. This includes a hard hat with battery-operated headlamp, which replaced the open flame carbide lamp worn by the early miners.
A nickel's worth of carbide in 1900 would last him about a week. You're going to put enough in there for about 2 hours. And so he has to have moisture. If he didn't have any water with him, what he would do, he'd spit in it. And you see the acetylene gas is what that's making. Now this thing is similar to a cigarette lighter, but the only way you can make it burn is put your hand there and let the gas build up. After you let the gas build up, then you hit it with your hand to make the flame. What he used back then was a cloth hat, and so this was kind of hard on his head, especially if he didn't look what was above him.
Safety glasses are an integral part of our safety protection equipment, obviously to protect the eyes from dust or while using hand tools and that sort of thing where flying debris could present an eye hazard. Eye protection was not a consideration in the early days.
Other items not available to the early miner include steel-toed boots, a portable methane monitor, and an apparatus called a self-rescuer.
A self-rescuer is a device by which a human can breathe in very low oxygen content atmospheres, and it will provide you the ability to breathe for a period of approximately 1 hour.
While there have been many changes in the way coal is mined, one thing has remained constant: the types of underground mines. Drift mines have a tunnel driven horizontally into the side of a hill to reach the coal. Slope mines are constructed when the bed of coal is relatively close to the surface, but is too deep to be recovered by surface mining. Shaft mines are the most common and generally the deepest, some as deep as 3,000 feet. Elevators carry workers and equipment in and out of this type of mine. A flat vehicle called a man trip takes miners where they need to go once inside these mines, and mine cars transport the mining machines in sections that are then assembled underground. Large automated machines and computerized controls have not only led to greater productivity, but they have also led to better health and safety for the miners, physically removing them from potentially hazardous situations. Although mining disasters have decreased dramatically in the last century, working in an underground environment will always have inherent dangers. In the summer of 2002, the entire country watched as 9 miners in Somerset, Pennsylvania were rescued after being trapped in a flooded shaft mine for 3 days. The miners tapped into an old abandoned mine that contained more than 50 million gallons of water that broke through. But these miners were the fortunate ones. A year earlier in Alabama, 13 miners died when part of the mine roof collapsed and caused a methane gas explosion. And there have been more tragic recent disasters in underground mines throughout the world. Next, while underground mining is still a vital aspect of coal mining, in the 1970s, technological advances would lead to new surface mining methods that would forever change the way coal is mined. Nestled among the desolate plains and towering mountain ranges of Wyoming is the North Antelope Rochelle Coal Mine in the Powder River Basin, the largest coal mine in the world. This surface mine produces more than 75 million tons of coal a year. Surface mines are extensively engineered and highly mechanized operations, accounting for 65% of coal produced in the United States. Most of the coal found in these mines is recovered, making surface mines twice as productive as underground mines.
What we have now is the development of a mining system, basically, which is incredibly cheap and incredibly productive. The idea that you simply peel away the surface of the earth to expose the coal seam.
Surface mines didn't appear until the late 1800s in Danville, Illinois. The great technological development in surface mining goes back to 1911 with the introduction of the Marion shovel, the first real stripping shovel.
Before World War II, surface mining wasn't the predominant method of mining because equipment wasn't big enough to move the massive amounts of overburden that have to be moved in a surface mine to get to the coal seam.
After the war, manufacturing processes led to the development of larger and more productive surface mining equipment. And by the 70s, the size of the machines increased dramatically. Surface mines also tend to be very safe because most of the work takes place above ground in large open areas, eliminating methane explosions and cave-ins. The coal is uncovered by giant earth-moving machines that strip off the overburden, the earth and rock covering the coal. The dragline has an enormous bucket suspended from the end of a boom, which extends more than 275 feet. Draglines are considered the world's largest land-based machines, some of which have 250-ton buckets that are large enough to park 2 Greyhound buses side by side.
This dragline removes approximately 75,000 tons of overburden each day. It will take about a month for that machine to mine from where he is currently to the far wall on the north end of the pit.
In most surface mines today, the overburden can also be blasted and broken apart by explosives placed in boreholes.
3, 2, 1, fire hole.
We use about 45,000 tons of explosives a year to blast about 240 million cubic yards of overburden. When the overburden is shot, we bring in either our major dragline stripping equipment or truck shovels.
The size of the equipment has increased to where we had a 100-ton truck. We have trucks now up to 400 tons to haul coal.
After the overburden is blasted and removed, the exposed coal is then loaded into trucks by electric power shovels that are 20 stories high. Huge trucks haul tons of coal, and covered conveyor systems deliver the newly acquired coal to nearby preparation plants. The cut in the mine is then refilled with the reserved overburden. The site is graded, covered with topsoil, and reseeded so that new vegetation can grow. Mining companies weren't initially required by law to reclaim the land until the 1977 Surface Mine Coal Reclamation Act.
What they did is they blast the rock above the seam, push it over the side of the mountain, expose the coal seam, remove the coal, and then just leave the whole lot behind them as an environmental disaster. With the passage of the 1977 Surface Mine Coal Reclamation Act, this was no longer allowed. And through a system of making the mining companies put up huge bonds, basically, they forced the mining companies to reclaim the land to original condition.
Surface mining, also called strip mining, has remained environmentally controversial despite the Reclamation Act.
Strip mining, particularly the way that it's being practiced in parts of West Virginia and Kentucky today with mountaintop removal, is literally blasting the tops off of mountains and dumping tons of rock and dirt into streams and valleys where miles and miles of streams are being obliterated. The government is not doing an adequate job of enforcing the environmental laws that are designed to protect the mountains and the valleys. The SMACRA Act is not being adequately enforced.
The mining companies claim that removing mountaintops and filling in valleys is the only economical way to get to the cleaner burning coal. While the government is eager to help the companies, environmentalists and residents living near the strip mines continue to fight them. In the meantime, new coal mines are still being developed. Years of planning are required before any extraction can take place.
Once you acquire a lease, then it might take up to 8 to 10 years just through the permitting process with the various state and federal agencies.
For both surface and underground mines, aerial and satellite photography, as well as radar and global positioning systems, are used in locating the coal deposits.
By using computers, we enter the information that we have from the aerial photography, and then the computer will calculate the volume of material that is within a given block that's proposed for mining. And that will tell us exactly how many yards of overburden we have to remove to get to the coal seam.
Once the coal is extracted, it needs to go through the preparation process. Rocks and other impurities need to be filtered out through various cleaning procedures. The coal also needs to be crushed, sized, and blended. Large pieces of coal are broken up into smaller pieces in machines called breakers and crushers.
and the coal is crushed to a size that most utilities utilize, and that's about 2.5 inches or smaller.
This size burns most efficiently in most power plants. The processing of coal involves an intricate network of electric motors, high-capacity belts, and sophisticated sensors, which are all linked to computers. After it has been washed, the coal is then dried in one of two ways. Either a machine spins the coal dry, or huge vacuum disc filters pull the water out. The coal is now ready to be delivered to the utility companies. 60% of all coal produced from mines is transported to its destination by railroads. A large portion is transported in unit trains, 100 or more cars that can be loaded and unloaded automatically.
The coal is conveyed to the load-out silos, and it's flood-loaded into trains at the rate of about 7,000 tons per hour. So a unit train that carries about 14,000 tons can be loaded in about 2 hours.
14,000 tons of coal is enough to power a city of 1.3 million for one day. Another method of transporting coal is by barges. Smaller amounts of coal are moved by truck or by conveyor directly from a mine to a power plant.
I've seen so many changes just in the last 10 years. I never thought we'd be using explosives to actually move the overburden. I never thought we'd see 400-ton trucks. I have no idea what the new technologies will be, but I'm sure we will be awed probably by the new technologies that will come out in the, just in the next 10 years.
Next, while extraordinary advances in coal mining have led to safer working conditions and increased productivity, the industry faces a much more daunting challenge. Now, it has to clean up its act. Coal has always had the reputation of being a dirty fuel. But the industry has developed new technology that can reduce the 4 pollutants naturally found in coal: sulfur, nitrogen, carbon, and mercury. The sulfur found in coal combines with oxygen when the coal is burned and produces sulfur dioxides, a major source of air pollution. Acid rain is believed to be another harmful effect of burning coal. The sulfur and nitrogen released into the air when the coal is burned can combine with water vapor and form droplets that fall to Earth as weak forms of sulfuric and nitric acid. But as a result of the new clean coal technologies, 95% of the sulfur and nitrogen in coal can be filtered out before they can escape into the atmosphere.
The Clean Air Act of 1970 provided standards for utilities to meet and essentially required us to develop many new technologies to better combust the coal. And so that act was a technology forcing act, and we're burning coal much cleaner today than we were prior to that law being passed.
One method the utility companies initiated was the use of flue gas desulfurization units, also called scrubbers. These scrubbers remove most of the sulfur oxides from the stream of gases produced by coal combustion before they go up the smokestacks. The flue gas is sprayed with an alkaline agent, such as lime or limestone. The chemical reaction forms calcium sulfate, which is then removed and discarded.
Scrubbers are applied at some power plants, and they can reduce emissions of sulfur dioxide by as much as 90%. But the problem is that there's hundreds of plants that aren't using a full suite of state-of-the-art control technologies, and they're emitting pollution at 4 to 10 times the rate that would be allowed for a new plant that was being built today.
Another available but not fully utilized new technology is the precipitator, which removes fly ash, the dark sooty material that results from burning coal. Precipitators are filters that electrically charge particles to trap and prevent ash from going up the smokestacks. These precipitators can eliminate more than 90% of the polluting elements. A pre-combustion method that can reduce sulfur content from coal by as much as 30% involves simply washing the coal after it is mined. The waste material is stored, and the water is recycled for future use by power plants. Sulfur emissions are also being reduced by the increased use of coal found in mines that are naturally low in sulfur. The coal in Wyoming's Powder River Basin, for example, is 10 times lower in sulfur than most coal from the Appalachian regions.
Using low sulfur coal from the West is only part of a comprehensive set of actions that are needed to clean up air pollution from coal combustion.
One of the reasons that we have been thrust to the forefront of coal production in this country is our low sulfur coal, but we also don't have to wash it. So many eastern and midwestern operations will have wash plants. We don't have wash plants.
Another problem associated with coal combustion is global warming.
Coal-fired power plants are the largest source of carbon dioxide in the United States. Carbon dioxide is a heat-trapping gas that accumulates in the atmosphere, forming a blanket that prevents heat from escaping. And that blanket is causing temperatures to rise all around the world and causing our climate to change.
Clean coal technology will address the issue of global warming by, one, burning the coal more efficiently, and we're also working on technologies that will sequester the carbon dioxide so that we can burn the coal and not put carbon dioxide into the atmosphere.
The U.S. is joined with other countries in researching various options for sequestering or trapping the carbon dioxide. One possibility involves directly collecting the carbon dioxide from power plants and pumping it into oil and gas reservoirs or on mineable coal seams. Electric utility companies have spent $70 billion on coal pollution control devices. Most recently, they are trying to find better methods of reducing toxic metals emissions, like mercury.
One of the clean coal technologies that we can use is gasification. And what that means is we can use a chemical process to convert the coal from a solid to a gas. It can be burned in a combined cycle process, so it can be burned at great efficiencies. So the source in the future of really clean power, reliable power, will be coal converted to gas.
The gasification of coal seems to be the one thing that everyone agrees upon.
The only technology that I know of that really has promise for making coal truly clean is integrated gasification, combined cycle technology, coupled with carbon dioxide separation and disposal to eliminate the harmful CO2 emissions that are contributing to global warming.
We still have close to 500,000 square miles of coal under our feet, enough to last us at least 250 years. With such a vital resource so abundant, the responsibility that comes along with consuming it grows. Further technological breakthroughs will be needed to minimize ecological damage. Hopefully, the industry, pushed by government, science, and environmental watchdogs, will find them.